Now let's look at common attacks, common network security attacks, and defense mechanisms. Okay, so the first attack is eavesdropping. As we saw in the previous video, that the internet we are using today is a public network. That means that any communications between two remote parties will have to go through routers controlled by the third party. Okay, so any data that you put in the network will have to go through other routers, and so that means any router. So that means on the path of your data from the source to the destination, on that path, any router can see your packets, your IP packets. Okay, so what you need is a common packet sniffer to find out what the contents of those packets are. For instance, you can use Wireshark. Okay, so this is a common network packet sniffer. You can also use TCP dump. Wireshark has a GUI interface, so which is a very convenient tool to use. Of course, it can also be used. It can also be used to analyze network traffics. Okay, and the solution to counter eavesdropping attacks is to encrypt your data. Okay, so that the routers on the path of your data won't be able to see the true content of your packets. The next attack is cryptoanalysis. So this attack is targeted at the underlying encryption algorithms and key generation algorithms and management. Okay, so the purpose of cryptoanalysis is to find useful information from encrypted data. For instance, one of the analysis would be to find out if the encrypted data has any statistical structure, because that statistical structure may reflect the same structure of the original plain text. Hence, a mapping could be made. So the defense mechanism for cryptoanalysis attack is to make sure this analysis conducting such analysis will be difficult to do. So for instance, you may want to use longer keys and stronger encryption algorithm. And of course, you need to manage this algorithm, and you need to have a robust implementation of these algorithms and manage these algorithms well. Particularly, you need to have a good data structure to store your secret keys, okay, and manage them. The next attack is password pilfering. Okay, so for any authentication to be done, the common mechanism is username and passwords. Okay, so this is to authenticate a user is and is legitimate. So password protection is often the first defense line, which may be the only defense available in some systems. Okay, but nowadays, for instance, you have other mechanisms to authenticate users. On your cell phone, you could have a retina scan, fingerprint scanned, and you can, maybe there are some others, right? So facial recognitions, that kind of things. But passwords are still the commonly used authentication mechanism. So the methods to steal or pilfer user password would be guessing, okay, social engineering, dictionary attacks, and password sniffing. So we're going to look at each of these possible techniques. Okay, guessing is the easiest way to steal a password, to find out a user's password once. So for instance, the following is a survey of commonly used passwords. Okay, this was done a few years back. A lot of users simply use some phrases or strings they can remember. Hence, when an attacker gets a file of usernames, and they can first try to see whether these commonly used passwords would match any of those usernames. Now, again, when we talk about security, network security, we don't usually mean the target would be a specific entity. Okay, so any machine will be the target. So let's say if you have 1 million usernames, and about 10%, oh, I'm sorry, 10% too big. Maybe you have 1 million usernames, and you have maybe 0.1% of users that use these common passwords. Okay, then of course you can get into a lot of users' accounts. Okay, so this is a guessing attack. The next attack is social engineering attack. Methods of using social skills to steal secret information. Okay, so these two are common techniques. One is physical impersonation. The attacker pretends to be a different person to delude the victim. Okay, so for instance, they may pretend they are some of the managers at the corporate headquarters, and they call a secretary in a remote office and saying that they needed to get into the system to see some data because there is a meeting going on, they need to cut a deal, but the computer he got into was down, so he couldn't see the data he used to be able to see. Now he wanted to see that data in a remote office, that kind of thing. So that is physical impersonation, social engineering. The other one is in an electronic form, which is called phishing. Okay, so this is the most common form of mass social engineering attacks. Okay, so basically what these attacks is to send you a disguised email message and and ask for your usernames and passwords, or send you a masquerade websites that look like a real website you usually go to, and then pop up a login window asking you for your username and passwords, and then of course the attackers can catch that information. Okay, so the textbook has a real phishing information example. I'm sure if you use internet a lot, you should have seen such phishing examples yourself. Okay, so this is a real phishing attack example. Okay, so in general, any phishing email would contain a link to a bogus website called a phishing site. Okay, so there are other forms of social engineering attacks. For instance, this is a common method you saw detectives would usually use, like you saw it from a TV series called Columbus, right? They collect recycled papers from recycling bins and try to find out information that may lead to your username and passwords. Or electronically, they can use a web browser pop-up, okay, pop up a login window and asking for user login directly. The defense mechanism is to use anti-phishing extensions of web browsers to prevent such pop-up windows from popping up on your screen. And of course, from the user's point of view, you should be very vigilant when you saw such windows pop up, and don't do it. Okay, so don't just type in your username and passwords when you see that window. Okay, the next password filtering attack is dictionary attacks. So the user passwords are stored in so on any system, they don't store user passwords in plain text. Instead, they store an encrypted version of users' passwords. Okay, so let me draw up something to show this. All right. So so usually you have a username and then password. So that password to the user is in plain text, but that plain text password is not stored on any computer system. Instead, so let's say this is W. Instead, it applies a hash function. Okay, so W is a plain text, and the encrypted version of this password is is h of W. H here is a hash function or cryptographic hash. So your username, let's say this is you, then this, maybe it's a WU, so indicate this password is for you. So this information gets stored in your computer. So when the user U logs on, he puts he enter his password, he enter his username, and then enter his password, and then the system computes H W sub U. So if this one, okay, so if this matches with this one, then of course the user U is authenticated. So that is the common mechanisms for storing passwords. Okay, in Unix and and Linux operating systems, passwords are stored in a file name, named shadows under this particular directory. So this is system directory /etc. In Windows XP and some other similar operating systems, passwords are stored in a file named SAM, which is stored in the systems registry. Okay, let me erase this, and then now we move to the next slide. Okay, so a typical dictionary attack proceeds as follows. First, the attacker needs to obtain information of usernames and the corresponding encrypted passwords, and then run the encryption routine H, okay, used by the underlying system on all possible passwords. Okay, so these possible possible passwords. So these passwords could be English words, names, dates, and some combination of these, and maybe also some numerical values. Okay, so these are possible passwords. Okay, so now let me draw up this again. Okay, so let's say the attacker gets a particular user and gets his encrypted passwords. So now he wants to find what this W sub U is. So what he can do, of course, he will try or possible W use. Okay, so let me put a prime here. Okay, try all possible passwords and then compute, because this H is public knowledge. So this routine is public because it is the standard things under the corresponding operating system. Try all of them, okay, and see whether this is equal to HW. Now, we know that this H is a hash function. So even though this particular W U prime may not be identical WU, but they have the same hash. So that would count too, because what you need to enter on the system is this, because this gets stored in the system. So you get WU prime and they have the same hash, then you will be allowed to get in. Okay, so that's a common method of dictionary attack. The reason it is called dictionary attack is you try all possible passwords, and one common way to get them is to get a dictionary, and that's also passwords people tend to use in early days. Okay, so but then from efficiency point of view, it has a problem. Okay, so the procedure I just described, you could either do it on the spot. So once you get a user name and password, and you try all possible passwords, so you do it on the spot. But then, you know, this takes tremendous time because there are so many possible candidates. So that takes time, okay? It's not efficient. Okay, the second is you pre-compute a you pre-compute a user a you pre-compute a table where you have a for all possible passwords, you pre-compute its encrypted value and store on the attacker's system, right? But then that's too big, right? So that table will be huge if you have to consider all possible passwords. And there is a technique to make this process more reasonable, which is a technique called rainbow table. Okay, so it helps reduce the table size and make computation manageable. All right, so the idea of rainbow table is the following. Now let me start a screen so I can draw up something. Okay. So as we said that, so what we want to do is to make dictionary attack manageable. You cannot do it on the spot by trying all possible passwords, and you cannot also pre-compute a table with all possible passwords because that will be too big. So the compromise would be I store part of the information. So here's the idea. So now let's say I have a user password W, which belongs to a set P that is a set of all possible passwords. For instance, if you use a dictionary, so P will be your dictionary. And of course, you can add some dates, you can add some names, and then of course you can enlarge that P. Then you can put some numbers, other symbols, right? So, but then of course this P could be huge. But nevertheless, what the idea is this. So I randomly select a W in P. Of course, let's say this is a legitimate user password, and what gets stored is on the system is H of W. Okay, the goal is to find W, and to find W in a more efficient way by taking a trade-off of space and time, right? So you do it on the spot, takes too much time. You do it you pre-compute every possible W, you have to store lots of data. So I want to find a middle ground. So then the idea is, first of all, we know W. So this is you. So H of W is longer than W. Okay, so maybe this W is 8 characters long, 10, 18, and so on, right? So usually it won't be too big, too long. But H of W tends to be longer because this H is a hash function. So then when I see this, in order to find a candidate W prime, I need to reduce this length. So to reduce this length, I am going to use something called a reduction function, R. So this is called reduction. Okay, so this reduction will hopefully, so this is a reduction function, will hopefully, when I apply R on this H of W, it gives me a password in P, okay? So that is the idea. So now what I would do is, as I said, I randomly select. So this is a randomly selected. So this is a selected at random. And then what I'm going to do is I'm going to start from W, and then I'm going to apply H. Okay, so let me say apply H. And what I'm getting is H of W. And then I'm going to apply R. I'm going to get, let's say I get W1. So that I hope is in P, okay? And then I do this a few times. Apply H again. I get H of W1 going R. I get W2, right? I do this a few times. So this is H of W2. I do this a few times. Finally, I'll get, let's say, I get Wn. And then apply H. I get H of Wn. Okay. Let me use K here, because N usually tends to be, people would think K is fairly big, but N would be fairly big a number. But well, of course, N, as long as you know N is some number, that would be fine. So let me just keep N here. All right, so then the idea then, now let's say what I need to store. So this is a train, right? So this is a train. So what I store is the beginning, W, and the end. Okay. Now, so why is this useful? So now, assuming I get H of, let's say I get H of W prime. Okay, so this is the password I got. Okay, assuming, okay, this W prime appears in one of these. Okay, so if W prime is in the string, in this chain, then I can find it by looking at this. Okay, so I start from W. I do this. I encrypt H, reduce it until I find until somewhere. Let's say this W2 is W prime. Then I can find it, and then I know this H of W2 is H of W prime. So this is the plain text I found, W2, right? So then I found this password. But however, of course, you know, this is the best situation. So it may not happen in this string. So that means I need to do more strings. Now, this string should not be too long, right? So this string, you don't want it to be too long. So this n should be manageable, should not be too big, should not be too big. Okay. So what happens if your W prime does not appear in the string? Okay, so that means you need to do more of these strings. So that is the idea of a rainbow table. Okay, so let's, so now I'm going to do a few of these. So I get W1, randomly selected. And then I do W2. And then I do a bunch of these. Let's say WM. Okay. And then I create a table, a train. So let me call it 1, because use this to get the intermediate ones, right? So you get H, you get R, you get a few times. Eventually you get to, let's say 1N. And then what I get to store is H of W1N. So each of these is a train. So this is H of WM. Let's say their lengths may not be exactly the same. Let's put N1 here, N2 here. Just indicate their lengths. Doesn't have to be exactly the same, but it's easier to have the same size for each train. So then what I get to store is this. Okay, I get W11. And the next value will be H of W1 and sub 1. W21, H of W2 and sub 2. So the last one, WM1, H of WM and sub M. So this is a rainbow table. So what I want, the ideal rainbow table, is that the ideal rainbow table is that none of these strings overlaps. No strings overlap. Okay, that's one. And I also hope this covers my possible password space. Okay, so that means all the intermediate. So all passwords, all possible passwords are covered in these strings. Oops, in these strings. So let me rewrite this. Okay, so that way I will be sure I can always find a password in this table. Of course, in reality, it is just hard to achieve, but nevertheless, you can, when you have a rainbow table, and I have captured H of W. So the idea then, to find out whether this W appears in one of these string by doing some computation, but not the entire thing. Okay, so now let me start new page. So we first want to see, let's say we got H of W. So this is captured. I capture this. Okay, so this is captured. And then what I want to is to try to see with, look at the table, the rainbow table, to see if there exists I such that H of W is equal to H of the ith row. Okay, so if it is, then I can hopefully, okay, I will start from WI1, and then, so this is H going to WI2 and so on. So this is I and I, H of I and I. And then I can, so this is the one I find. Okay, that gives me the same hash function. Okay, so this W, as I said, may not have to be the same as this one, as long as the hash is the same. So if there is no such I, so if no such I exists, so what you want to do is now we get, so this is HW is what we get. I'm going to reduce its length and then apply H. And then repeat the process to see whether there is one last one, there is one row, one train, okay, that even though such I exists, and then we find and try to find if there is J such that after this it's equal to H of Wj and J. Now this J could also be I as well, okay? If this is true, then you can start, okay, from that J, and then you can find your passwords. Okay, so how long you have to do this? The ideal situation is that you only need to do the maximum of Ni times. There you can stop, because after that, if none of these matches, then you will know your password will not appear in these strings. Okay, so that is the idea of using rainbow table to launch a dictionary attack. Now let's go back to our slides. So I already explained how rainbow table works. So these are just formal writing of what I explained earlier in on a whiteboard. Okay, so the last attack will be password sniffing. So this has to do with the network communication. If you do a remote logins and you put in your username and passwords, if that password is not encrypted when it's sent out, and the attacker just needs a let's say sniffer, network sniffer, right? A Wireshark, by putting in its own router on the path you would go through, then he will be able to learn your password. Okay, if the password is encrypted, then of course he needs a dictionary attack. All right, so what would be the defense method? Of course, encrypt all messages, including login information, using SSH and HTTPS, because your passwords will be encrypted. But as I said, even the passwords are encrypted, you they are still can be learned by dictionary attacks or guessing, right? So that means we need to make sure our passwords are complicated enough to defy any dictionary attack. Okay, so there are several rules you may want to follow. So rules to help protect passwords from pilfering. Number one, use long passwords with a combination of letters, capital letters, digits, and other characters that you can find on your keyboard. $, pound sign, at, or semicolon, that kind of thing. Okay, do not use dictionary words directly. Do not use common names and dates. And do not reveal,